Key characteristics of equal sets. So in the last section, we laid the groundwork by introducing what sets are, those collections of distinct objects. Now, we're going to build on that foundation and really get specific. We want to understand exactly what it means for two sets to be considered equal. It's important to understand that two sets aren't just similar or alike. They need to meet very particular criteria to be truly identical. Think of it like identifying twins. They look very similar, but they have to have the same characteristics to be considered identical. Over the next few slides, we'll carefully outline those characteristics, step by step, so you can confidently determine whether two sets are equal or not. We'll make sure it's all clear and easy to follow. We'll be looking at examples so you can see these concepts in action. What does it mean for sets to be equal? So we've talked about what sets are in the previous slides, and now we're going to really nail down what it means for two sets to be considered truly equal. Here on this slide, we're defining equality between sets. We say that two sets, let's call them set A and set B, are equal, and we write this as A equals B, if and only if they contain exactly the same elements. That if and only if is important. It means both conditions must be met for the sets to be equal. Now, what does exactly the same elements actually mean? Well, it breaks down into two key things. First, they must have the same number of elements. In more formal mathematical terms, we call the number of elements in a set its cardinality. So, both set A and set B need to have the same cardinality, the same number of items inside them. Second, and this is equally important, the identical elements condition. This means every single element that's found within set A must also be found within set B. And every single element in set B must also be in set A. Think of it like a perfect matching. No extras, no missing pieces. Now, a really common mistake students make is thinking that just having the same number of elements is enough. It's not. You need both conditions to be true. We'll see that illustrated in the examples coming up. Finally, and this is a crucial point about sets, the order in which you list the elements doesn't matter at all. Sets are what we call unordered collections. So, whether you write a set as 1, 2, 3, or 3, 1, 2, it represents the exact same set. We'll reinforce this with examples on the next few slides, so you can really get comfortable with this concept. Breaking down the characteristics with examples. So we've now established what it means for two sets to be equal, same number of elements, and those elements have to be identical regardless of order. Now, to really solidify our understanding, let's move on to looking at some examples. This slide simply states that we're going to illustrate those characteristics, the ones we just discussed, with several examples. We'll start with sets that are equal, so you can see those conditions met. Then, we'll look at sets that are not equal, so you can clearly identify where things go wrong. We'll break down each example step by step, checking both the number of elements and the elements themselves. This will help you practice applying the rules we've learned and build confidence in determining whether two sets are truly equal. In the following slides, you'll see sets labeled with capital letters like A, B, C, and so on. Remember, these are just labels to help us refer to the sets easily. The content within the curly braces, that's what defines the set. So, pay close attention to what's inside those braces as we work through the examples. We'll be building on this foundation as we move forward, so make sure you understand each example before we proceed. Example 1, equal sets. Let's move on to our first example to really solidify what we've discussed about equal sets. On this slide, we have two sets, A and B dollar. Remember, that's just a way to label our collections of elements. Set A dollar contains the numbers 1, 2, and 3. And set B dollar contains the numbers 3, 2, and 1. Now the question is, are these sets equal? As we learned, simply looking similar isn't enough. We need to systematically check if they meet our two key characteristics. First, let's check the number of elements. Set A dollar has 3 elements, 1, 2, and 3. And set B dollar also has 3 elements, 3, 2, and 1. So the first condition, having the same number of elements, is met. Great. Next, and this is crucial, we need to verify that the elements themselves are identical. Let's start with set $1. We need to confirm that every element in $1 is also present in $. So, is 1 in $? Yes. Is 2 in $? Yes. And is 3 in $? Yes. Now let's do the reverse. Let's check set $. Is 3 in $? Yes. Is 2 in $? Yes. And is 1 in $? Yes. Since all the elements of $1 are in $, and all the elements of $, are in $, we've satisfied the second condition. Therefore, because both conditions, the same number of elements and identical elements, are met, we can confidently conclude that set $1 is equal to set $. We write this as A equals $. And importantly, notice that the order in which we listed the elements didn't matter at all. Sets are unordered collections. \1, 2, 3 $$ is the same set as \3, 2, 1 $. This will be important as we move forward and look at examples where sets are not equal, which we'll do on the next slide. Example 2. Equal sets with different representation. So let's move on to another example to really solidify our understanding of equal sets. On this slide, we're looking at two sets which we've labeled C and D. Set C contains the elements B and C, and set D contains the elements C, A, and B. Now remember from the previous examples and what we discussed earlier, we need to check two things to determine if these sets are equal. First, we need to verify the number of elements. Let's do that. As you can see, both set C and set D each have 3 elements, so that first condition is met. Good. Next, and this is the crucial part, we need to check if the elements themselves are identical. This means every element in C must also be in D, and every element in D must also be in C. If you look closely, you'll see that A is in both, B is in both, and C is in both. We've confirmed that all the elements of C are present in D, and all the elements of D are present in C. Therefore, because both conditions, the same number of elements and identical elements, are satisfied, we can confidently conclude that set C is equal to set D, which we write as C equals D, and importantly, notice that the order in which we listed the elements didn't matter at all. B, C is the same set as C, A, B. Remember, sets are unordered collections. This will be important as we move forward and encounter more complex examples, like the ones we'll see on the next slide where sets aren't equal. Example 3, non-equal sets. So now let's shift gears and look at some sets that are not equal. This is just as important as understanding equal sets, because it helps solidify what we've already learned. Here we have two sets. Let's call them set E, and set F. Set E contains the numbers 1, 2, and 3. And set F contains the numbers 1, 2, and 4. Now let's check if these sets are equal, remembering our two conditions. First, let's look at the number of elements. Set E has 3 elements, and set F also has 3 elements. So, they pass the first test, but as we discussed earlier, having the same number of elements isn't enough on its own. Let's move on to the second condition, identical elements. If we carefully compare, we see that 1 and 2 are present in both sets. However, 3 is in set E, but it's missing from set F, and conversely, 4 is in set F, but it's not found in set E. Because these sets don't contain exactly the same elements, we can definitively say that set E is not equal to set F. We denote this mathematically, as E is not equal to F, remember. Even if the number of elements matches, a single differing element is enough to prove the sets are not equal. We'll continue to build on this understanding in the next few examples, so pay close attention to how even a small difference can make sets unequal. Example 4, another non-equal set. Let's move on to our fourth example, and this one really highlights a very quick way to determine if two sets are not equal. We're looking at two new sets here. Set G and set H. Set G contains the elements 1 and 2. We can write that as G equals the set containing 1, 2. And set H contains the elements 1, 2, and 3, so H equals the set containing 1, 2, 3. Now let's check if these sets are equal. Remember, we need to satisfy both conditions, same number of elements and identical elements. Let's start with the number of elements. Set G has 2 elements, right? 1 and 2. Set H, on the other hand, has 3 elements, 1, 2, and 3. Because the number of elements in set G and set H are different, we can immediately conclude that these sets are not equal. We don't even need to bother checking if the elements themselves are identical. If the cardinalities, that's just a fancy word for the number of elements, are different, the sets cannot be equal. So, we write that G is not equal to H. This is a really important time saver. If you quickly see that the sets have a different number of elements, you know right away they aren't the same set. We'll reinforce this idea on the next slide with a summary of the key takeaways, so keep this in mind as we move forward. Key takeaways. Let's recap everything we've learned about equal sets with these key takeaways. First, and this is crucial, two sets are equal if and only if they have the same number of elements and contain exactly the same elements. Think of it like a perfect match. Both the quantity and the specific items within the sets must be identical. We saw this in our examples. If even one element was different, the sets weren't equal. Next, remember that the order of elements within a set does not affect its equality. This might seem a little strange if you're used to lists, but sets are unordered collections. So, a set containing 1, 2, and 3 is considered the same as a set containing 3, 1, and 2. We demonstrated this with sets A and B, and C and D. Rearranging the elements didn't change the fact that they were equal. Now, let's consider a quick shortcut. If two sets do not have the same number of elements, they absolutely cannot be equal. We don't even need to bother checking the individual elements in that case. As we saw with sets G and H, it's an immediate disqualifier. Finally, and this is where students often stumble, if two sets do have the same number of elements, but those elements aren't identical, then the sets are not equal. Remember sets E and F. They both had 3 elements, but because they contain different elements, 3 versus 4, they weren't considered equal. Keep these points in mind, and you'll be able to confidently determine whether two sets are equal or not. In the next slide, we'll address some common mistakes students make when working with equal sets, so pay close attention. Common mistakes. A common mistake students make is focusing solely on the number of elements. While having the same number of elements is necessary for equality, it is not sufficient. The elements themselves must also be identical. Now, what does this mean? Remember from our earlier examples, we first checked if two sets had the same cardinality. That's just a fancy word for the number of elements. It's a good first step, absolutely. But as we saw in example 3 and 4, just having the same number of elements isn't enough to guarantee the sets are equal. You also need to confirm that every single element in one set is also present in the other. If even one element is different, the sets aren't equal. So, checking the number of elements is a necessary condition, but it's not enough on its own. It's not sufficient. Another mistake is being misled by the order of elements. Remember, sets are unordered, so 1, 2, 3 is the same set as 3, 1, 2. This is a really important point. We saw this demonstrated in examples 1 and 2. Sets don't care about the order in which you list the elements. Whether you write a set as 1, 2, 3, or 3, 1, 2, it represents the exact same collection of items. So, don't let the arrangement of the elements trick you into thinking the sets are different when they're not. Let's move on to this final slide, where we discuss some common pitfalls students encounter when working with equal sets. All right, that concludes our discussion on the characteristics of equal sets. Hopefully, you now have a solid understanding of what makes two sets truly equal, and you're aware of the common mistakes to avoid. Remember to always check both the number and the identity of the elements, and don't get hung up on the order.